Hey everyone, my name is Rohawk, and in today's video, we're going to be discussing and implementing the k-means clustering machine learning algorithm in Python with the Scikit-Learn library. While classification and regression-based methods are what often come to mind when we think of AI, unsupervised learning is no less important, where patterns are learnt from untagged data. Clustering is one of the most widely known examples of this approach, with applications ranging from image segmentation to cybersecurity. Well, enough of me talking. Let's get right into the code and start exploring. Welcome to the programming section of this video, where we'll be implementing the k-means clustering algorithm in Python entirely from scratch. As always, if you would like to follow along with this tutorial, the link to the Kaggle dataset that we'll be exploring can be found down in the description below. Feel free to check it out. Without further ado, let's get started. First, let's import pandas for data frame manipulation and matplotlib for data visualization purposes. Perfect. Next, we'll import the label encoder class from scikit-learn's preprocessing module and the k-means class from scikit-learn's cluster module. Both of these imports will be used later on for data preprocessing and data clustering. So, after printing the first 5 rows of our data frame out to the console, we yield the following data frame. And here we can see all of the different attributes or features included within our dataset. Here, it's also worth noting how a spending score with numbers ranging from 1 to 100 is generated based off a variety of factors, including annual income and gender. However, before we can go any further, we need to perform some data preprocessing on our existing dataset. For instance, notice that the gender column is non-numeric and string-based, with its values being male and female as raw strings. Since we want to measure correlation numerically, we need to convert this categorical variable into its more usable numeric representation. How do we do this? Well, let's find out. First, we have to create a new label encoder object, which will be used later on to assign numeric values to different class values. Next, we can perform the label encoding by calling the fitTransform method on our gender column and assigning the result back to our original column. Perfect. So, if we view our newly modified data frame, we yield the following result. And here we can see that a male gender is represented by the number 1 and a female gender is represented by the number 0. With our data preprocessing stage out of the way, let's now perform some data visualization on our mall customers dataset. To start things off, let's first graph a simple scatterplot that models annual income against a spending score. Since an individual's annual income would naturally be the most determinant of their spending ability, this is a great place to start. So we can do this by simply calling the scatter method and passing in both of our attribute columns in for x and y respectively. So here, as you guys can see, our x data is made up of the annual income column and our y data is made up of the spending score column. Additionally, to make our plot more readable to someone who isn't really familiar with our mall customers data, I've added some axes labels and a title. So here, if we click run, we yield the following scatterplot. And we can see that our data definitely contains a few clusters. There's a concentrated cluster of data points in the very middle and a couple of other groups on the edges of the plot. However, whenever we train a k-means clustering model, we pass in the number of clusters we want to represent as a parameter. Since this is unclear at a first glance, we don't know how many exact clusters are present. Thankfully, we can use an elbow plot to understand the optimal number of clusters for our data. The elbow plot determines the optimal value of k in a k-means algorithm by calculating the sum of squared distances for each unique cluster value within a range of numbers. Once this has been determined, we plot the number of clusters on the x-axis and the sum of squared error on the y-axis to narrow down on the elbow of the plot, which represents the data point after which the sum of squared error began to decrease in a linear fashion. For now, however, we will create a new list representing all of the cluster values that we want to test and set it to a list including numbers from 1 to 15 inclusive. Next, let's declare and initialize a new list called results to store the number of clusters and the sum of squared error for each test run. With that all aside, we can now iterate over each number in our clusters list using a simple for loop. Inside, we'll create a new k-means classifier containing the given amount of clusters. which is done by setting the n clusters hyperparameter to our loop variable. After this, we will fit our model to the annual income and spending score columns like so. Now we can append a dictionary containing the number of clusters and the sum of squared errors for our classifier. Here, notice that we are able to access the SSE value by accessing the inertia field of our model. After our for loop is complete and the results list is populated with data, we can convert the list to a pandas data frame by simply calling pd.dataframe on the results variable and storing the data in a new variable called resultsdf. Finally, if we print out our data frame, we can see that we yield a new dataset that contains the number of clusters and a corresponding sum of squared error value for each unique cluster amount. To visualize an elbow plot of our number of clusters against the sum of squared error, we can first plot a line of our results as well as the individual data points in a different color. So I first made a call to the plot method so that we could get a line modeling our elbow plot, and then I made a call to the scatter method so that we could see the individual points along that line. Here, it's also important to notice that I specified the z order hyperparameter to be 2 for the data points, since I want them to show up on top of the plotted line. After adding some axes labels, a title, and a legend to our plot for increased readability, we can finally view our elbow plot. So after running our code, we get the following elbow plot. And here, as you guys can see, we have the number of clusters on the x-axis and the sum of squared error on the y-axis. Unsurprisingly, our plot is in the shape of an elbow, and we see that the cluster number of 5 looks to be the elbow of our visualization. We can say this because after x equals 5, all of the following sum of squared error values decrease in a linear fashion. So we conclude that 5 clusters are the optimal amount for our data. Now we can create a new k-means classifier and pass in 5 for the n clusters hyperparameter, since that is the number that will help us model our data in the most accurate way. Additionally, we can call the fitPredict function on our model to generate predictions for each data point in our graph. So here, as you guys can see, in my call to the fitPredict function, I passed in the annual income and spending score columns from our data frame. So after printing out the final predictions list, we can see that we just get a bunch of numbers. But what does this all really mean, and why should we care? Well, each number correlates to a specific cluster grouping, which can be validated by the fact that the predicted values range from 0 to 4 inclusive. 0 represents the first cluster, 1 represents the second, 2 represents the third, and so on. Now, to use these predictions, we can simply add them as a new column in our data frame. So now, if we visualize our newly modified data frame, we get the following result. And as you can see, on this far right hand side, we have a new column called clusters, which represents our model's predicted cluster for each individual data entry. Another thing I find really interesting about the k-means classifier is the fact that you can access the cluster centers or centroids by accessing the cluster centers field of the model. So here, if we run our code, we get 5 XY data points representing the centroids for all 5 clusters within our k-means classifier. To visualize our clusters, their centroids, and the overall distribution of the data, we can start off by creating separate variables representing the columns for each unique cluster. Here, it's also super important to notice that we do this by taking all of the rows in our dataset where the value of our cluster column is equal to a particular number between 0 and 4. After generating these cluster-specific data frames, we can plot each one in a different color. So here, I've simply plotted the annual income against the spending score for each cluster for all of our different datasets. Finally, to plot our cluster centers, we can simply access the x and y values in our cluster centers list, specify their marker as a star, set their color to black, and increase their overall size to 300 so that we can see them better in our scatterplot visualization. Additionally, we can finish off our scatterplot by adding some axes labels and a title to make our plot more readable. Now for the moment of truth, seeing our final cluster diagram. So, there we have it, a full scatterplot representing all of our unique clusters in different colors and their corresponding centroids. This is k-means clustering in action. And just like that, we've implemented the k-means clustering approach in Python entirely from scratch. By leveraging features like the elbow plot, sum of squared error, and centroid measure, we were able to visualize each individual cluster and give it statistical meaning. Yet another example of the transformative potential of machine learning. If you enjoyed this short tutorial and feel that it helped you out, feel free to like the video and subscribe to the channel to learn more about technology's unique applications to social good. Aside from that, thank you so much for watching, take care, and I'll see you in the next one.